So this lesson is on Pascal's triangle. So we're going to explore Pascal's triangle and discover certain patterns within it. And more importantly, we're going to be able to use some of the numbers that are within Pascal's triangle for some practical purposes. So the first thing that we'll do is I'll show you how to create Pascal's triangle from scratch, and then briefly identify some of the patterns that are in there. And then more importantly, once we get to expanding the power of a binomial, we're actually going to use Pascal's triangle as a shortcut along with other patterns that are within the expansion of a binomial that will help us do that more quickly than it would be in a brute force method. So the first thing we'll do is actually go through and create Pascal's triangle. So Pascal's triangle starts with a 1 at the very top, and then down the sides. So as we go down, or what we say as we add additional rows, we're going to add another number to it, and the ends of each row are always going to be 1. So Pascal's triangle is always going to start as a 1 and a 1. And as we go down to the next row, again, the ends of a row always has a 1. And how do we get the terms or the numbers in the middle is that we're actually going to take the rows above and we're going to add it. So in this case, we take that number and that number, we're going to add it. And in this case, 1 plus 1 will give us 2 for that row in Pascal's triangle. So the next row, we continue that same pattern. We have 1s on the end. And then we're going to take the two numbers above it, the cell that we're sort of doing. So in this case, this one and this one, we're going to add that. So 1 plus 2 is 3. And the next one, the next number in this row, in the third row, is, again, we're going to take those two numbers, add them together. So 2 plus 1 is 3. It would sort of follow that pattern. So we're going to keep following that pattern. And I'll continue on for a couple more rows so you can see sort of what's happening. So 1s are going to be at the end. And how we get the numbers, the terms in the middle, is that we're going to take sort of this number that we want, and we want to the upper left and the upper right, add those two numbers together. We're going to get 4. These two we're going to add together. We're going to get 6. And then these two together, we're going to add, and we get 4 again. And let's do another row. So 1 on the outside, 1 on the outside, and then in the middle. So we have to follow that algorithm or that pattern. So those two numbers added together, 1 plus 4 is going to be 5. In this case, 4 plus 6, that's going to be 10. 6 plus 4 is going to be 10 as well. And then this one, 4 plus 1, is going to be 5. And just one last row I'll do for us. And then this pattern could continue on and on. And I'm sure you could Google images on websites and you see Pascal's triangle with a lot more rows than what I'm going to show you. But the idea is that from this, you should be able to generate Pascal's triangle on your own, just using the pattern and the algorithm that I'm showing you. So here, 1 plus 5 is 6. I'm going to add these two numbers to get this next number in this row, which is 15. Add those two, we're going to get 20. Add those two, we get 15 again. And if I drew this nice and symmetrical, the triangle will look a lot better. But essentially, that's what it looks like. So we could go off and sort of explore some of the patterns that are within Pascal's triangle. So I'll just sort of highlight these in green. One obvious pattern is sort of we get the 1, 2, 3, 4, 5 numbers increasing by 1. So that's one pattern. We sort of look at that slant in Pascal's triangle. Another cool pattern that we kind of see in here is what I call the hockey stick pattern. So it doesn't matter if you go left or right, but in this case I'll go from left to right. And wherever I stop, if I go immediately to the left, and again, if I did this nicely, this would have seen a little bit better. We see a little hockey stick. So 1 plus 2 plus 3 plus 4 equals 10, the number 2 in the other direction that we're going down. So here we could do this, even this hockey stick as well. 1 plus 3 plus 6, that will give us 10 as well. So there's these hockey stick patterns that also exist in Pascal's triangle. Kind of neat. But the other patterns I really want to explore with you is one is recognizing that the numbers are symmetrical. So for example, in this row, we got 1, 6, 15, 20, and then we got back down 15, 6, and 1. So it has that sort of symmetry. Even for rows that have an even set of numbers or terms, you get 1, 5, 10, 10, 5, 1. So it's symmetrical in that sense. Just some of the definitions that we could talk about in referring to Pascal's triangle is we could look at what we call row number. So here we could say that there says a row number. And in this case, we're actually going to start with row 0. So row 0 actually has one term in it, or one number. In this case, this is going to be row 1, row 2, row 3. Oops, I should have slanted this more to the side. Row 4, row 5, and row 6. So that's how you sort of label the row numbers in Pascal's triangle, starting at 0. On the other side, another neat pattern that we can kind of see is, maybe I'll do this in blue, is if we add up the numbers in our row. So here, if we add up all that numbers, obviously we add up 1, it's just 1. I'll do this in the farther right, so hopefully we can see the pattern is happening over there. I'm going to do this in red. If I add up these rows, the numbers in that row, obviously 1 plus 1 is 2. Adding up that row, 1 plus 2 plus 1, that's going to be 4. 1 plus 3 plus 3 plus 1, so this row, the third row, that adds up to 8. And then this row, the fourth row, 1 plus 4 is 5, plus 6 is 11, plus 4 is 15, plus 1 is 16. So hopefully we do see a pattern that's coming down in terms of the sums of the rows. We can almost predict that the next one is going to be 32, and the next one is going to be 64. So you can see that the sort of starts at 1, it starts doubling. So it goes from 1, 4, 8, 16, 32, 64. The other cool thing is that these sums have a connection to the row number. And if we can kind of see is that we take the row number, this is really the 2 to the power of that row number. So this is really 2 to the power of 1. This is same thing as 2 squared. This is going to be 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, and 2 to the power of 6. So here the exponent matches our row number. Okay, so that's also another interesting aspect of Pascal's triangle. That's actually a little bit more useful if you take data management and we talk about combinations, that Pascal's triangle reappears again. So the next example I want to take us through is triangle. Those numbers look familiar. So this is sort of one of the things that is kind of fourth row of Pascal's triangle. That's this over here, 1, 4, 6, 4, 1. And look, fifth row of Pascal's triangle is there. So then the coefficient is going to be 1, 5, 10, 10, 5, 1. Using Pascal's triangle to expand a binomial. But before we get there, we're going to just do it in the old-fashioned way in terms of just expansion. And one, to sort of refresh, I guess, ourselves on how that's done. But maybe more importantly is recognizing sort of the difficulty behind it. So let's just start off with a plus b to the power of 1. Well, that's simple. That's just going to be a plus b. A plus b quantity squared. We get fooled into thinking that maybe this is a squared plus b squared. At this point in the game, hopefully we're not making that mistake. It's not that straightforward. We confuse that with maybe a difference of squares. So that's not how that expands. So here we'll do it brute forced, and sort of using the FOIL method if we think back, or just the distribution called the rainbow method. So a times a is going to be a squared. Then we're going to get a times b, which is ab. And then likewise, we're going to get plus ab plus b squared. So that simplifies to a squared plus 2ab plus b squared. I'll go through this one last time to recognize as the exponent goes up how much more difficult this becomes. So here, if I do a plus b quantity cubed, well, I'm going to shortcut it and saying this is really a plus b quantity squared times a plus b. So we discover that a plus b quantity squared is a squared plus 2ab plus b squared times a plus b. And now we go off and expand that. This is now a trinomial times a binomial. We have to do 6 multiplications, and then I'm going to simplify. So bear with me as I go through this. So this is a cubed. And then I'm going to do a squared plus times b. Then the next term we're going to get plus 2a squared plus b. Oops. 2a squared b, I mean. And then plus, so 2a times b is going to be 2ab squared. And then we're going to distribute the b squared. So that's going to be ab squared plus b cubed. And then we need to collect like terms. So here we're going to have an a squared plus times b. And we have another 2a squared plus b times b. So it's going to be a cubed plus 3a squared b. And then these two are like terms. So that's going to be 3ab squared. And finally, the last term, we got b cubed. So here we recognize that if something is cubed, we get 1, 2, 3, 4 terms. So going back a little bit, something is squared, we get 1, 2, 3 terms. And if something to the power of 1, a binomial to the power of 1, obviously we only get 1 term. Sorry, 2 terms. So do we see a pattern here? Do we see a pattern? So I'm going to highlight a pattern that if you may see it or you may know it already, but if you don't, it's not so apparent. So I'm actually going to write the coefficients. Here, the coefficients is going to be 1 and 1, so that's really 1a and 1b. What's the coefficients of this term? Well, that's 1, 2, and 1. What's the coefficients of this term, or this polynomial over here? 1, 3, 3, 1. And if we look back at Pascal, about Pascal's triangle, so we could actually use it for a binomial expansion. So I'm going to sort of, on the next example, I'm not going to expand it out completely, but in this case, I'm going to use it to establish the pattern that we could do to expand a binomial using Pascal's triangle. So here, we got a plus 4 to the power, sorry, a plus b to the power of 4. We recognize we're going to get 5 terms. So the first thing I like to do is, I know it's going to be something like AB, 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 AB. So we know we're going to get 5 terms. So the exponent on A is actually going to start with n. So we're actually counting backwards. So here there's going to be 4, 3, 2, 1, 0. And then for the exponent on B, and I'll use a green marker for this, is that we're actually going to start from 0. So 0, 1, 2, 3, 4. So that's in its simplicity. That's what we do for the exponent. And then for the coefficients, what we do is we take whatever row that we have for Pascal's triangle, and we're just going to take the numbers from that row in Pascal's triangle, and that becomes our coefficient. So here we're dealing with 4. Sorry, yeah, 4. So we're going to take those coefficients, and that becomes the coefficients for my terms. And we're going to add them all in there together, and it becomes like that. So basically what we discover, a plus b to the power of 4, this comes out to, if we simplify it, a to the power of 4 plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus, well, a to the power of 0 is just 1, we get b to the power of 4. Okay, so that's how we could quickly use Pascal's triangle and then another pattern with the exponents to quickly expand a binomial. So let's go through some more. Let me go back to difficult examples and how we can take advantage of that. So here we have m minus n to the power of 3. Here we got a subtraction in here. So it's not a plus b, but it's a minus something. So an easier way to think about this is I'm going to let a equals m and let b equals minus n. Okay, so here we're going to get a plus b essentially. So it comes back to something that we're familiar with that we just did up above. So we know that this is going to expand to, again, I'm going to do my exponents and my variables first. So a is going to start at 3, b to, actually I'm going to write all my ab's first. That's the pattern I like to do. So AB, I got, this is the power of 3, so we get 4 terms. And it'll be all addition in between. And again, I'll start my exponent for B at 3, 2, 1, 0. And with B is going to start from 0, and go 1, 2, 3. And once you sort of get the hang of this, you don't have to go through this explicit step. But to me, it's kind of nice because we sort of establish the patterns and see what the patterns in there. And then what's the third rule? Pascal's triangle. So I've done it enough already that I remember it's going to be 1, 3, 3, 1. So those are my coefficients. So what does this simplify to? Let me just write the simplified version here. This is going to be a cubed plus 3a squared b plus 3ab squared plus b to the power of 3. Now I'm going to replace what I have with a and b with the actual the values that we substitute it with. And this is where we can see where there's a bit of a difference. So here, substitute m for a. So this just strictly becomes m cubed plus 3m squared. And now this is the tricky part. We need to substitute a negative n for b. So here we get 3m negative n squared. And notice what I'm doing with the brackets is that it's all of negative n squared. And then finally replacing b with negative n. So again, all of negative n cubed. So this is going to come out to, we simplify this now, is going to be m cubed. Well, negative n turns going to be turned the positive 3 to a negative 3. So that's going to be minus 3m squared n. A negative n squared is just going to be a positive n squared. So this stays as positive. So we have 3m n squared. And then negative n to the power of 3 is going to give us a negative n cubed. So the trick or the process that we want to kind of go through when it's not strictly a plus b is we do want to sort of define those variables a plus b. So I substitute that in so we get the normal expansion, and then plugging what we replaced, or so what we let a, b in back into our equation and doing some expansion on that to get our full equation. So the next example is a little bit more tricky, because now we're going to deal with a non-1 coefficient in front of our variable. So here, again, we're going to let a equal 2x in this case, and let b equal 3y. So now this becomes a plus b to the power of 5. And here I'm going to quickly do Pascal's triangle. So here, actually, I'll still do it explicitly one last time so you can see what's going on. So here, because the exponent is 5, I'm going to get 6 terms. So it's going to be plus in front of all these, or in between all these. And the exponents are going to go from 5, 4, 3, 2, 1, 0 on A. And on B is going to start from 0, 1, 2, 3, 4, 5. I should have left some room for the coefficients. I'm going to have to squeeze that in. So for fifth row of Pascal's, so it's going to be 1, 5, 10, 10, 5, 1. Not the best looking job there, but hopefully you can still read that. Now let me kind of simplify this. So this is going to be a cubed, or a to the power of 5, plus 5a to the power of 4b, plus 10a cubed b squared, plus 10a squared b cubed, plus 5ab to the power of 4 plus b to the power of 5. Now we replace our values back in for a and b. And really the important part that you want to remember here is to have that in brackets. So in this case, it's going to be 2x to the power of 5 plus 5 2x to the power of, to the power of 4. B is 3y plus 10 times 2x cubed plus times 3y squared plus 10 2x quantity squared times 3y quantity cubed plus 5 times 2x times 3y to the power of 4. I'm going to squeeze this in down here. Finally, 3y quantity to the power of 5. So now we have to go off and expand all these, which again, we have to be sort of careful with our exponents. So it's not just going to be 2x to the power of 5, but it's the whole quantity 2x to the power of 5. So I have to do 2 to the power of 5, which is 2 times 2 is 4, times 2 is 8, times 16 is 32. So 2 to the power of 32, x cubed, x to the power of 5, plus 5, well, 2 to the power of 4. Oops, I realized I missed a bracket over there. So this is the tricky thing about Pascal's triangle, is we need to be careful, is this is really 2 to the power of x all to the power of 4. So here, 2 to the power of 4 is 16, x to the power of 4. And then here we're just still left with 3y. 2x cubed, so 2 to the power of 3 is 8. X cubed, 3 squared is going to be 9. So there's going to be 9y squared. Then the next one is going to be 10 times, well, 2 quantity squared is going to be 4x squared. 3 cubed is 27. Y cubed. I'm running out of room. Next one is just going to be, so I'm just going to expand that. That's going to be 10x. And then 3 to the power of 4 is 81. Y to the power of 4. And then finally 3 to the power of 5 is going to be 243. And then y to the power of 5. Then last one step is we have to clean up our coefficients. So this stays at 32x to the power of 5. Then we have 5 times 16, which is 80, times 3. So that's going to be 240 x to the power of 4y. Then we have 10 times 8 times 9. So 8 times 9 is 72. Times 10 is 720 x. That looks like a 5, but that's a 3. X cubed, y squared. Then we're going to have 24 times 7, which is going to be 108 times 10. So that's going to be 10,080 x squared y cubed. And then finally 10 times 81 is going to be 810 y to the power of 4. And then our last term stays as 243 y to the power of 5. So it's still a bit of work to expand to the power of 5, but much, much better than if we were to just go through and do our distribution across expanding the polynomials. Okay, so that's that one example, and I think there's one last. The homework gets a bit tricky because now our coefficients is not just 1, but there's a negative there. But at least it's the power of 3, so hopefully that makes your job a little bit easier. So we're gonna, so we got a and b in our polynomial, so I'm going to choose some different variables. So in this case, I'm going to let x be a over 2, and let y be 2b squared. So this now, it's going to be negative 2b squared. So now this becomes x plus y to the power of 3. So I'm going to quickly expand this. This is going to be x cubed plus 3x squared times y plus 3xy squared plus y cubed. Then we go replace x with our values here. Remembering to put them in brackets so that we remember to take the power to the proper value. So it's going to be a over 2 to the power of 3 plus 3 times a over 2 squared times y, which is a negative 2b squared, plus 3, x is a over 2, and y is negative 2b squared, and this time we're squaring that. And finally, we're going to get negative 2b squared all to the power of 3. Go off and apply my power laws to the exponents. So here we're going to get a cubed over 8 plus 3 times what a squared over, sorry, a over 2 quantity squared is going to be a squared over 4. And then negative 2b times negative 2b squared. And then plus 3a over 2. So I'll just do that. And then negative 2b squared quantity squared is going to be 4b to the power of 4. And then finally the last one is negative 2 to the power of 3 is going to be negative 8. And then b squared to the power of 3 is going to be to the power of 6. And now we're just going to go back and clean up everything now. So this stays as a cubed over 8 plus 3 times negative 2 is going to be a negative 6 over 4. So that's going to be a negative 3 over 2. Negative 3 over 2, a squared, b squared. And then over here, this next term, 3 times 4 is 12 divided by 2. So that's going to be leaving me with a positive 6ab to the power of 4. And then the last term is just minus 8b to the power of 6. So that's what that expansion looks like. Actually a little bit easier and faster than the previous one. It's only tricky because we have fractions and then negative in there. But at least it's only to the power of 3. So that's how we make use of Pascal's triangle to expand a binomial.